Assalamu alaikum. This presentation is on voice jitter, the cycle-to-cycle perturbations in the fundamental frequency and fundamental time. In normal persons producing a vowel continuously, the fundamental frequency of successive glottal cycles would be expected to be quite close. The time taken for each cycle from the start of the cycle to the end would be very similar to the time taken by the successive cycles with only a very minor variations, usually less than 1%. The voice jitter is defined as the variation in the voice fundamental frequency from cycle to cycle while producing a vowel continuously, and usually reflects a lack of control of the vibrations of the vocal folds. It's expected to be higher in patients who have voice pathologies than the average jitter in normal individuals while producing a vowel, where the variation should be between 0.5 and 1%. In this presentation, we shall go through the sources of the voice frequency perturbations, what causes a higher than usual voice jitter. We'll also go through the values for the jitter in dysphonia patients and in normal voices, and how to quantify the variability and the fundamental frequency, the jitter, by 4 different parameters. We shall also go through the clinical relevance of the perturbation measures, and will end up by discussing the speech fundamental frequency variability as opposed to the variability and the fundamental frequency while producing a vowel. The voice jitter has received a considerable amount of interest and research, perhaps more than any other single area of acoustic voice analysis. This had started in the 1960s with observations from von Leyden and Moore, and also from Lieberman, who had noticed that the commonest observation in the pathological conditions is a strong tendency for the frequent and rapid changes in the regularity of the vibration of the vocal folds. This was assumed to be one of the most important causes for dysphonia. But what causes this voice frequency perturbation? Broadly speaking, the origin of these fundamental frequency variations can be either neurological, due to fluctuation in the action potential of the laryngeal muscles from cycle to cycle. It can be biochemical, due to fluctuations in the distribution of the mucus on the vocal folds, and also asymmetry of the vocal folds structures in terms of length and mass and tension. They can be aerodynamic due to fluctuations in the flow emerging from the glottis, or they can be acoustic due to the irregularity in the source vocal tract interactions during phonation. In normal individuals, for example, a male producing a modal voice uttering the vowel ah continuously, you could see on the top chart here the very fine irregularities in the fundamental frequency from cycle to cycle. These variations in the fundamental frequencies are much coarser if the patient has a hoarse voice, as you can see in the bottom chart. What are the expected values for jitter in patients who have dysphonia and in normal individuals with normal voice? This report from Entry Hospital in Manchester shows the values for jitter in normal individuals, where the value is generally less than 1%. Only one single individual had a jitter value of about 2% while having a normal voice. On the other hand, patients who have a hoarse voice had a much higher values for jitter. Only one single patient with a hoarse voice had a jitter value about 2%. So generally speaking, the jitter values would be expected to be much higher in patients who have hoarse voice compared to patients who have normal voice, in whom the jitter typically varies between 0.1% and 1% of the fundamental frequency period. What is the correlation between jitter as an objective measure of voice and the subjective grade of hoarseness? You could see from here that with low grades of hoarseness of voice, you would expect low grades of jitter percentage as well. But with higher grades of dysphonia, like in 8 or 9, you could see wide variations in the percentage of jitter for the same grade of hoarseness. Like, for example, grade 8, it varies between maybe 4% jitter and about 17% jitter for the same grade of voice. The relationship between jitter and the subjective hoarseness grade is not linear. You could see all these dots scattering away from the diagonal straight line. Perhaps about 50% of the hoarseness can be explained in terms of jitter. This is the effect size in here. So jitter is not universally correlated with hoarseness, and the validity of the jitter percentage test and even its reliability has been questioned by some authorities, particularly in severely dysphonic voices. How is the jitter quantified? What are the ways of measuring the jitter perturbations? There are 4 quite related parameters to quantify the jitter. Number 1 is the mean or the absolute jitter, the jitta, and it's measured in milliseconds per cycle fundamental time. The other 3 are measured as percentages of the average fundamental time. This can be either percent or relative jitter, the jitt, or the relative average perturbation, the RAP, or the 5 points period perturbation, and we'll go through them all one by one. Starting with the simplest of the parameters, the mean jitter or the jitta or the absolute jitter. This is the simplest of the parameters and it is measured in milliseconds. This example would illustrate how it is measured. If you have 5 different glottal cycles with different fundamental times for each of these cycles, the way to measure the variability and the fundamental time or the fundamental frequency by the jitta or the mean jitter is to subtract the difference between any 2 consecutive cycles, this cycle and the second, or the second and the third and the fourth, and the fourth and the fifth. You just subtract the duration of the fundamental time of consecutive cycles, and then you take the average of these 4 differences in milliseconds, and that is the mean jitter or the jitta, and it should be less than 83 point something milliseconds. This is the first parameter. Next is the percent jitter, the local jitter or the jitt. It's based on the notion that the mean jitter, as we have just been through, is very strongly correlated to the average fundamental time of each cycle. So it's common to express the jitta as a percentage of the average fundamental time. We start by calculating the jitta as the average difference between successive cycles, cycle 1 and cycle 2, cycle 2 and 3, 3 and 4, and so on. Take the average of these cycles in milliseconds divided by the average fundamental time of the cycles and express it as a percentage, and the threshold for pathology, for being normal or pathology, is about 1% for the jitt. This would show the percent jitter variation in relation to the gender and to the vowel produced. The fundamental frequency of females is higher than fundamental frequency of the males, with slight variation while producing different vowels like either an A or an E. But there is obvious variation, differences between males and females. There is also some significant variations in the jitter percentage between females and males while producing the different vowels. As you can see, you would expect higher jitter values in females in relation to the jitter values in males. And then there is the relative average perturbation jitter, the RAP. In contrast to the mean or the absolute jitter, in which we take the average of the differences between individual cycles, the first and the second and the third and the fourth, and we take the averages. Here we consider 3 cycles at a time. We find the difference between this cycle, fundamental time, and the average fundamental time of these 3 cycles together, and divide this by the average fundamental time for these 3 cycles, and then we move to the next 3 cycles. We take the difference between the cycle in the middle and its 2 neighbors, and find out the difference between fundamental time here and the average of the 3 together divided by the average fundamental time of the 3 together, and then move and so on. And this would give the relative average perturbation, the RAP, and the threshold to detect pathologies here would be 0.68%. And finally, there is the 5-point period perturbation quotient jitter. Here we take, rather than taking individual differences or consider 3 cycles together, we consider 5 cycles together. The cycle in the middle and the 2 before and the 2 after. We find the difference between the fundamental time for this cycle in the middle and the average fundamental time for the 5 cycles together divided by the average fundamental time for the 5 cycles, and move to the next and so on. The average of these 5-point period perturbation quotient should give a percentage less than 2.04%. What is the clinical relevance of the jitter perturbation measures? Although some investigators have reported positive findings, that is to say that high jitter would be associated with a high degree of dysphonia, this is not a straightforward relationship, and there is no consistent evidence that a jitter measure can sort out patients by diagnostic category. There are many reports that confirm the initial reports of Lieberman that you would expect higher degrees of jitter in high grades of dysphonia, but there is no clear consensus on the clinical relevance of the perturbation measures. Now, to add to the uncertainty and the clinical relevance of the perturbation measures, there are also some methodological concerns. These concerns are based on 3 things. The first is that we are measuring a phenomena that is quite small, something below 1%. So it's difficult to be very precise in measuring something that is quite small as such. There is also difficulty in very precise determination of the onset and the offset of individual cycles. Machine-based softwares would sometimes have problems in the exact determination of the onset and the offset of different cycles, particularly in patients who have marginally periodic voices. But these are the very patients that you are more interested in getting an objective measures of their variability and fundamental frequency. And there are also concerns about the different software systems used in measuring jitter don't always agree. Some pairs of them could agree up to 0.8, which is quite or reasonably high correlation, but others would not correlate at all or would correlate at a very low level like 0.23. So it was difficult to compare results obtained from one software system to another. The variability and the cycle-to-cycle changes in fundamental frequency producing a vowel is different from the variability and the normal speech fundamental frequency variability. To measure the speech fundamental frequency variability, we use another set of parameters, including the pitch sigma, which is basically the standard deviation of the average cycle, the distance between all the cycles, and the average cycle for the speech period. And this fundamental frequency variability is reflected here as a standard deviation. So that's one way of measuring speech rather than vowel fundamental frequency. The next question would be, for how long does this individual uses certain frequencies? Which frequencies is he using most? Which frequencies he is using less? How long he would use high frequencies, and for how long he would use very low frequencies. For this, we convert the speech fundamental frequency contour into a speech fundamental frequency histogram, where the x-axis are frequencies and the y-axis at the time spent during voicing these frequencies. The x-axis is divided into columns called frequency bins. These columns have a very narrow frequency range, and every time the speaker uses this very narrow range, it would be included into the corresponding column. The columns are equally spaced according to the octave, the semitones, and the quarter tone scale, because this is how we perceive changes in the vocal pitch. So we would know from this that this individual speaker had used these two frequency bins, this narrow frequency range, most of the time, and he uses less the very high frequencies and the very low frequencies. We can also estimate which frequencies he is using for 90% of the time by excluding 5% here and 5% there, or 80% of the time by excluding 10% here and 10% there. So we know something about the frequencies he is using most of the time. But a better way of identifying variabilities in the speech fundamental frequencies is this: the difference between DFX1 and DFX2. DFX1 is the histograms we have been through so far, which identifies how often a certain individual would be using certain narrow frequencies. So if he is using these frequencies most of the time, the average or the mean speech fundamental frequency would be here, and he uses higher and lower frequencies less. This is marked here as the red histogram. On top of the red histogram, you can overlay another histogram, the DFX2, which contains in these bins the pair of successive frequencies that have been used during the utterance of this frequency. So all the frequencies in this column would be analyzed if the successive of the following frequency for all these frequencies are no higher or no less than 10% from the first frequency, then it can be counted in the second histogram, the DFX2. So the closer the second histogram to the first, the better, because that would indicate that successive frequencies are quite close to each other, which gives a smooth voice, a smooth vibratory frequency change, and a good voice. So this would give an idea about how close are the successive frequencies to the original frequencies obtained from the DFX1. And the closer the two together, the better for the voice. The coherence percentage is the number of the samples in DFX2, the black plot, divided by the total number of the samples in the same bin on the DFX1 bin, multiplied by 100. The closer the number of samples in the black to the number of samples in the red, the better for the voice. So if you have very low coherence, then this would indicate poor voice quality, because there is quite a difference between individual vibratory cycle frequencies and the preceding or the following frequency. Another way of plotting the regularity or the irregularity of the fundamental frequency is this scatter plot, the CFX plot, in which the frequencies, all the frequencies, are plotted on the x-axis, and the immediately following frequency would be plotted on the y-axis. So say if we have a point here, a frequency at a point 100 Hertz, the following cycle, vibratory cycle, if it has an identical frequency or quite close to it, the plot, it will be plotted somewhere close to the diagonal line in the scatter plot. But if it has a widely different frequency, the successive vibratory cycle has a widely different frequency, it would be off the diagonal line somewhere in here, for example. So at the end, if we have all the frequencies plotted against all the succeeding vibratory cycles frequency, if we end up with a neat line along the diagonal here, this is normal voice. If we have much scattering of plots around the diagonal, then this would indicate a degree of irregularity of the speech fundamental frequency. So this scatter plot, the CFX1 plot, reflects the cycle by cycle change in the vocal folds vibratory frequency. If the succeeding cycles have very similar vibration frequency, they would all lie close to the diagonal in here. These are scatter plots of a patient who had recurrent laryngeal nerve palsy before the thyroplasty and after the thyroplasty. Now, before the thyroplasty, you can see how the points are scattered away from the diagonal. Things had improved after the thyroplasty, and now most of the dots are aligned either along the diagonal or quite close to it. So you would expect a better voice in this condition than before the thyroplasty. And this scattering of the diagonal be quantified? Yes, there is a coherence percentage here in which the number of points off the diagonal by more than 3% either ways are counted against the total number of the dots. and if this number is much less than 100%, then this would identify the degree of irregularity of this condition. You would expect things to have improved here, with the number of plots off the diagonal are much less and much closer to the diagonal, so this would give an indication about improvement in the regularity of the vibratory cycle. By this we come to the end on this presentation on the measuring the cycle to cycle variability in the fundamental time and fundamental frequency, either during producing a continuous vowel, the jitter, or in normal speech as the speech fundamental frequency variability. Assalamu alaikum.